A very good morning to all the participants and our distinguished speaker. I welcome the wonderful audience for today's Talk 6 of webinar series on electron microscopy titled Defect Structure of Germanium 111 on epitaxial gadolinium oxide 111 on silicon 111 heterostructures grown by molecular beam epitaxy. I will begin with an overview of SAFE IIT Bombay, which was inaugurated by our late ex-Prime Minister Shri Morarji Desai. Instrumental methods of analysis form an indispensable aspect of any research and development program. The Department of Science and Technology set up the sophisticated analytical instruments facility in different parts of the country. The main objective of setting up these facilities was to provide guidance in acquisition of data using sophisticated instruments. Professor Anil Kottantharail is currently heading our CRNTS department. SAFE IIT Bombay has several analytical instruments and provides measurement services to IIT Bombay users and to users from other colleges, universities, national laboratories and various industries as well. The current slide shows the list of instruments funded by DST in which two of the electron microscopes have been highlighted. The one at the bottom is an upcoming facility, a dual beam focused electron and ion beam which will be installed soon. The next slide shows the list of instruments which come under the central facility funded by IIT Bombay. Today we are going to highlight the three transmission electron microscopes. One of them is a conventional TEM and the other two are field emission gun based instruments with different analytical capabilities. Like the 200 kV FEC TEM has energy dispersive spectroscopy attachment with it, and the 300 kV FEC TEM has EDS and EELS as well. All are in-house at SAFE CRNTS. We have created a LinkedIn account for SAFE IIT Bombay. We would be happy to connect with you through this mode too. This is the brochure for the webinar series on electron microscopy, which is uploaded to this LinkedIn account. Following slide shows the staff at SAFE CRNTS. We would be happy to welcome you at SAFE and help you with the sample analysis. Talk 6 in the webinar series on electron microscopy will be shortly given by Dr. Krista R. Kiangte. It's a great pleasure for me to welcome Dr. Krista R. Kiangte. He obtained his doctoral degree from the Department of Physics, IIT Bombay in 2018 and continued working as a postdoctoral research associate in the Department of Electrical Engineering, IIT Bombay till September 2019. After that, he worked as a postdoctoral fellow in the Department of Physics, University of Arkansas, United States till July 2020. Recently, he joined Department of Physics, Institute of Science, Banaras Hindu University as an assistant professor. His research interests include molecular beam epitaxy of group 4 heterostructures for photonics application. Presently, he is working on integration of group 4 heterostructures on 3-5 systems. His work, in particular introduction of epitaxial high K dielectric in between two semiconductor epilayers, has drawn attraction in the MBE growth of group 4 research community. In addition to the MBE growth, he intensively works on characterization of epitaxial systems by high-resolution X-ray diffraction and high-resolution transmission electron microscopy. So let us commence today's webinar. Over to you, sir.
Okay, thank you so much, Mayuri, for a very nice introduction. Good morning, everyone. So today the topic of our talk will be defect structure of germanium on epitaxial gadolinium oxide, which is on silicon heterostructures grown by molecular beam epitaxy. So here you may see that the topic of my talk is very specific, and it may not go very well with the the topic of our series lectures, which is electron microscopy. However, since electron microscopy is to do with structural characterizations, it is always important to connect dots with other methods like XRD, RHEED, so on and so forth. So interestingly, while I was working in electron microscopy lab in IIT Bombay, what I used to observe was that the scholars who had prior knowledge on other structural characterizations like XRD can easily understand the concept of microscopy physics. So since XRD also works on the principle of kinematic scattering of X-rays, so electron also works on the principle of kinematic scattering of electrons. So understanding both helps a lot in characterizing any samples that you are working on. So today I would like to give a talk which consists the applications of reflection, high electron energy diffractions, X-ray diffractions, and transmission electron microscopy for structurals and mainly for defect characterizations of epitaxial heterostructures. As I said, the topic may be very specific, but I hope this will help you, how to, correlate the TM results with other techniques. Okay, so as we already, listened to the introduction part, so interestingly, I have a dual identity. Well, I got an invitation for this talk. I was working as a postdoctoral fellow in Department of Physics, University of Arkansas, United States. I work with Professor Gregory J. Salamo, who is very famous mainly with droplet epitaxy. But I got an assistant professor position in the Department of Physics, Banaras Hindu University, Varanasi, India. I joined this position recently, so officially, my place would be Department of Physics, Banaras Hindu University, Varanasi. Okay, now let us move quickly into the topic. So this is how epitaxy of germanium is done on gadolinium oxide silicon system. So the gadolinium oxide epilayer was grown on silicon 111 by MBE. By MBE, yeah. And we have grown the germanium epilayer over that epilayers by MBE in IIT Bombay. The process of the growth is no much different with other growth methods. We have done degassing, heating of the substrate in the growth chamber for cleaning the surface for the subsequent growth of the germanium epilayer. And the germanium epilayer was grown at 550 degrees centigrade at a growth rate of 1.6 nanometer per minute, which is roughly around 360 nanometers. So here in this talk, I may mention some technical terms which may be little, which you may not be familiar with. So so that technical term is type A and type B of heteroepitaxial system. These are nothing but the relationship in the heterostructures of the epitaxial system. So the normal to the 1 bar plane is indicated by an arrow here. All right. So here, if you rotate the interface of the two layer, okay. let's say like this. Here, if you consider the interface of the two layer as a mirror plane, you can superimpose one arrow with the other. Okay, right? So basically it means that, see, if you look the geometry from this side here, okay, now from the other side, and look this from this side, so it will have the same structures. All right, so this is done by 180-degree rotations of this arrow. If you rotate 180-degree, so basically you'll get the same structures, meaning the same directions. All right, so basically this is the mirror image of this one. So this is called type A and this is called type B of the heterostructure system. So this is nothing but it's just a rotation of your, your 111 plane system with respect to, 111 normal plane. So it's very simple. Okay, so as we go along, you'll understand this. So now coming to RHEED evolutions. So this is called reflection high energy electron diffractions. RHEED is a technique used for characterizing the surface, crystal structures, and morphology of the epilayer during the growth. Since the mechanism of the scattering is elastic, the diffraction pattern can be cast into the geometrical construction of the Ewald spheres in reciprocal space. All right, so the Ewald spheres of a two-dimensionals will consist of reciprocal rods like this. Yeah, when the rods of the reciprocal lattice intersect the Ewald spheres, the diffraction of the diffraction is satisfied and the diffraction pattern is observed on the fluorescent screen. So basically this is a two dimensions, you will have a reciprocal rods, but this is basically a 2D. So no, sorry, it's an islands or basically a 3D. So you're getting a spotty pattern. So this is a very important and useful tools. In fact, the physics is almost the same as, it is more or less the same as electron microscopy, but as I said, it is mainly used for, characterizing the surface and the morphology during the growth. So here is the RHEED image recorded for different stages of the growth of the germanium on that system. So if you look at carefully at 52 degree seconds of growth, a substantial change in the RHEED pattern occurred. So this spotty pattern suggests the onset of 3D island formations, characteristics of Volmer-Weber growth mode. So here a closer look at figure C reveals a superpositions of two spotty patterns. Here, these can be superimposed here, right? If you look at carefully, one of the pattern is significantly, has a lower intensity. So if you consider this as a mirror plane, yeah, it can be made to coincide with each other. Basically, if one of them is mirrored about the central rod, this rod, you can flip this here, you can have the mirror image here. So basically, this is what we called, stacking A and stacking B. So the observed superpositions of these two spotty patterns are attributed to coexistence of type A and type B in the epilayer, in the grown epilayers. And also it is interesting to note that after 70 seconds of the growth, the intensity of one of the two spotty patterns is strongly enhanced over the others, suggesting a preferential growth mode and hopefully type A. So a two-dimensional layer by layer growth is recorded after the germanium growth equivalent to around 10 nanometers, which is like 370 seconds of the growth. So this is how we quantify the defect structures from RHEED. Okay, and basically we are trying to correlate with our TM result. So this is the structural characterizations by using high resolution X-ray diffractometers. So here is the wide omega-2 theta scan of the bare substrate. This one is for the bare substrate. I hope everyone understood about XRD physics. So basically, you in wide omega-2 theta scan, or basically omega-2 theta scan or theta-2 theta scans, your reciprocal lattice vector is moving in a direction more normal to your crystal, your epilayer surface. So you can scan all the way from from any angles you want. So here we have done a wide scan just to check whether it is single crystals or not. So here the Bragg positions of silicon 111 superimposed with gadolinium oxide 222. So we have seen the same reflections for these planes at the same Bragg angle. So basically this is because the lattice constant of gadolinium oxide is twice the lattice constant of silicons, and both has the same cubic structures. So from the XRD data of the whole epitaxial system, meaning including germanium, here you can see only the Bragg reflections of germanium 111. So this clearly shows that the epilayer is single crystals. Okay, and to qualitatively estimate the crystal structure quality, we have done omega scan for 111 and 333 reflections for germanium, and it comes out to be 0.8 degree, which is quite reasonable. This implies that the crystal quality is okay. I hope you know how omega scan was done. So basically here your reciprocal lattice vector will be moving more or less parallel to your crystal planes, and this is the best way how you can quantify, quantitatively quantify the crystal quality. Okay, now coming to a very important portions, which is XRD pole figure analysis. To probe the epitaxial relationships and structures of defects in the heterostructures on a global scale, systematic pole figure measurement were performed. So here the diffraction intensity is measured by rotating the sample in beta directions while keeping the diffraction angle fixed. So basically this is phi scanned at different value of chi. So phi scan, basically it means that you are giving a polar scan by tilting your sample. All right, keeping your Bragg's condition fixed for a particular plane. If you don't understand, you can ask me during the questions and answer hours time. So here figure A and figure C are the pole figure recorded for silicon 111 and germanium 111 Bragg conditions, whereas B and D are their corresponding schematic diagrams. So here, if you look at carefully, S0, S1, S2 and S3, this one, and this one, they corresponds to 111, 1 bar 11, 1 bar 1 and 1 bar, basically a family of 111 planes in the silicon cell. So these basically reflect the threefold symmetry of the silicon 111 in the silicon 111 axis. So however, at the same value of alpha, basically at the same azimuth, you have another triad of spots, which is O1, O2, and O3. Basically, this triad. Okay, so these triads wherein the neighboring spots are separated by 120 degree corresponds to 2 bar 2 bar true and 2 bar reflection of gadolinium oxide. So basically it is a 2 family of planes. So basically these reflect the threefold symmetry as well for gadolinium oxide. However, here it is important to note that this dryite, okay, this dryite is rotated by 180 degree with respect to silicon 111. With respect to silicon S1, S2, and S3 dryite. These indicate that gadolinium oxide stacking sequence are of type B with respect to silicon on the global scale. So that's what I have already established and told you by using RHEED characterizations. Okay, now coming to figure C. So here we find another hexites. This one, GA1, GB1, GA2, GB2, GA3, and GB3. Basically, these. So this is at the same value of alpha, that is at 19 degree 0.5. Here it is important to note that the trite GA1, GA2, and GA3 are more intense than the other trite GB1, GB2, and GB3. So this reflects that the epi-germanium 111 layer is predominantly, they are of type A stack with respect to silicon 111 substrate. So it can be concluded that the type B regions represent rotational twins formed due to 180 degree rotation of the 111 plane about the 111 normal twin axis. Okay, so basically it means that you have germanium which have the same stacking sequence with silicon as well as gadolinium oxide. Okay, now very important portion. In addition to rotational twins reflections, we also observe reflection twins in the epilayer. So if you look at here carefully, you have GT naught, and this GT naught. It is represented by this tri. Yeah, I hope you can see this. So this means that these spots corresponds to the reflection from the germanium 111 family of planes, which are tilted by 38.9. Basically, it means the angle between this point and this point is 38.9 with respect to the global germanium 111 plane. So this is your reflection twins. There are also another three trites, this trite, and this trite. It's a GT1, this is GT1, in which one of the appeals lies outside the detection range of the pole figure measurement, that is basically 19.5. So basically these are symmetric with this. Okay, so GT1, GT2, and GT3, they are symmetric with GT0. So basically it means that, say for example, for GT1 trite, so these are appearing due to reflection twins of germanium 111 family of planes, making an angle of 38.9 with respect to 1 bar 1 plane as a global plane. Here they are making an angle of 38.9 with the global 111 plane. So here they are making an angle of 38.9 with respect to 1 bar 111 plane as a global plane. Okay, so basically we identify two types of reflections, namely rotational twins and reflection twins, and this is on a global scale. And so basically we will try to quantify these results and try to see the consistent of this result by using TEM. Okay, to obtain a quantitative estimate of the ratio of the global type A to type B regions for the germanium 111 epilayer, we perform theta to theta scan diffractograms at alpha equal to 19.5 and at different beta value as shown by the circle. Okay, so here the fraction of type B germanium within the epilayer is about 0.8. That is an amount equivalent to 3 nanometers, which is consistent with our RHEED observations. Okay, and here is the theta to theta scan for your reflection twins, which is basically a lamella of 115 oriented plane. So basically we are going to see this with our TM. Okay, now coming to the most important slides, and in fact this is the last slide. Okay, and my talk is very simple, and this is mainly for people who really wanted to work on TM and use them for structurals and defect characterizations. Here I wanted to say something which you may find it very debatable. In fact, we used to have a very intense and heated debate, yeah, with our colleagues. Though HRTM or TM is in general is very useful for structurals or defect characterizations, sometimes it can be very misleading because the area of interest is now very localized, or simply it is very small. Okay, so you cannot claim the result whatever you got in TM is for a global scale. All right, so it is always advisable to check your result by using other means of characterizations when you can see the result on a global scale. Okay, so I hope you understood what I'm trying to say. So I am saying that when you try to claim something for the whole epilayers or for the whole thin films or for the whole nanostructures, taking the result of TM sometimes may not be very convincing, or in fact, in other way around, it can be very misleading. So I'm saying that it would be very wise. It would be nice, or it would be, something interesting if you can, prove the consistency of your result with other, techniques like, XRD and so on and so forth. Okay, here the epitaxial relationships and defect structures were further analyzed, basically, mainly analyzed because you can see through directly by your own eye and by using HRTM. Basically, this is a cross TM section. The image recorded over a large area of the sample shows high density of stacking fold or twins and threading dislocations. Here it is important to note that the stacking fold density is lower in the upper half of the epi layers. So basically it means for those material science, if you grow a higher thickness, basically it means that you'll have more, you have a better crystal quality, which will help you to get a higher performance device. Here in figure B, we have high resolution image of the heterostructures, basically for the whole heterostructures. The type A and type B stacking sequence of germanium and silicon, they are the same. And this is what we have found in RHEED as well as by XRD, basically by using pole figure measurement. Yeah, the normal to the 1 bar plane here indicated for each regions are indicated for each regions, that is for silicon, that is for gadolinium oxide, and as well as for germanium, which reveal that the stacking sequence of germanium and silicon are the same, and whereas gadolinium oxide is rotated by 180 degree. So basically when we said rotated by 180 degree, so it means that it means that your 111 plane is rotated about 111 normal by simply 180 degree. So this is what we have previously already established by using RHEED as well as pole figure analysis. In fact, I have done TM analysis first, and in fact, I should have put this slide first and try to prove the consistency and try to explain the consistency by using RHEED as well as by using mainly by using pole figure analysis. Okay, so here is the close-up image for stacking fold or twins, as we have here in the one that we have here in figure A. So it is observed that the 111 crystal planes within the lamellar regions are inclined with respect to 111 planes of the surrounding unfolded germanium epilayers by an angle of 38.9. This is interesting, isn't it? This is interesting, really interesting. And in fact, this is what we have already get by using, what we have already got by using pole figure analysis. So the lamellar regions of this is it is a 115 oriented 111 plane basically. So you can see it here how we depict here schematically. Okay, so yeah, that's it. The stacking sequence of germanium and gadolinium oxide, they are of type ABA, and we have reflection twins as well as rotational twins here. By using TM, we get basically, as I said, I have done this TM characterization first, and I check the consistency of this result by using pole figure analysis. So yeah, that's it. With that, we come to the end of our talk. But what I try to send a message to all the audience who are listening, basically who are starting their career with electron microscopy. I would advise you to look into the how powerful the electron microscopy characterization is when you combine it with other structural characterizations like XRD, or if you have facility even with reflection high energy electron diffractions. So this will give you a very consistent result, and in fact your analysis would be very powerful. Okay, with that I come to the end of my talk. Thank you so much for your patience.
Thank you, Professor Krista Kiangte. Now let's begin with today's question and answer round. The first question is by Dr. Rohini Mandare. She wants to ask whether there are any structural changes occur if we change the substrate for deposition, example FTO or ITO or silicon.
Yes, definitely there is going to be change in your epilayer structures when you have different substrate structures, because whenever you think of the growth of epilayers on the substrate, meaning the growth of any nanostructures, so what important is the structures of your substrate as well as the thermodynamics of the growth, which is mainly governed by your substrate surface. So the energy obtained, or the energy given by the surface of your substrate is different for different crystal structures. So basically, if you have different crystal structures, there is going to be a change in your epilayers. Say for example, if you have a very high lattice constant and you try to grow a very small lattice constant over it, then there is going to be a change in your crystal structures. You may not even have a single epilayers. For that case, you may have high polycrystalline, meaning, or high defect crystals. So yeah, definitely there is going to be a change when you change your substrate. Say for example, indium titanium oxide. So I don't exactly know the crystal structures. So definitely it's going to be different from silicon, because as I said, the growth thermodynamics is governed by the crystal structures as well as your your film surface energy. So definitely there is going to be change.
Okay, thank you. How we choose the MB substrate?
Yeah, that questions is very similar to the questions asked earlier. Yeah, that's a very interesting questions. But don't worry, when you really work on the growth of any heterostructures, then definitely you will make your own choice. So yeah, in our case, we work on the growth of group 4 heterostructures on silicon, and sometimes we choose germanium. But however, we choose in such a way that the crystal structures, the symmetry is still maintained. Basically means if you want to grow a cubic crystal, then you have to choose a substrate which have a cubic crystals and which have almost the same lattice constant. However, if you think of gadolinium oxide, they are also cubic crystals. However, it is cubic bisbite, but it's more or less the same when you think on the surface of the gadolinium oxide. And if you look carefully, as I discussed during my HRXRD slide, you can see that the lattice constant of gadolinium oxide is mm, twice the lattice constant of silicon. So in that case you can have a lattice match. So yeah, depending upon your work, definitely when you start working you'll have a very good choice of your substrate. Please don't worry about it. Okay.
Okay. Another interesting question is to know the impact of the defect structure on the optical and electrical characteristics for the heterostructures.
Yes, that's a very important question. Before that, if you look at my work carefully, we have introduced, high K dielectric, that is gadolinium oxide, between the two semiconductors, that is silicon and germanium. So actually, this high K dielectric is blocking, the the current which is coming from the substrate. Basically, it will takes a very long time to go all the way from the substrate to your anode or cathode or whatever. So that will definitely uh, hamper the device work. So the main work of this introduction of gadolinium oxide in between the two semiconductors is to improve the performance of the device, be it photodetectors or whatever. So you just want to increase the performance of the device. So yeah, coming to your questions. So yeah, the trading dislocations or any kind of dislocations, be it twins or reflection twins, rotational twins, whatever you get, yeah, that definitely hamper the device performance. So if you look at carefully the first figure of the HRTM image, so half of the epilayers, below half of the thickness of the epilayers, are hugely populated with stacking fold and threading dislocations. So basically that invoke that if you grow a very thick epilayers, definitely then you will have a very good crystal quality, which will eventually help you in getting high performance device. Yes. Yes, actually, that's the whole purpose of having MBE. Suppose if you grow the same layer by using, say for example, sputtering, then you will have a huge defect. So yeah, controlling the quality of your epilayer is very important to control the performance of your device.
Thank you. Another advantages and principle of MBE, how is it different from ALD?
Yes, MBE is a very sophisticated instrument. Yeah, the heart of MBE is that it has a very high vacuum. So basically, if you have a very high vacuum, means that you have a very lengthy mean-free path for your other atoms to travel. So basically, it means that you can precisely grow whatever nanostructures you want. Maybe quantum well, quantum wire, quantum dot, or simple epilayer, so on and so forth. So yes, MBE has a lot of advantages. However, it's costly and sophisticated. Yes, if you think of most of the electronic device that we are currently using, all those are grown by MBE because you can precisely control, manipulate, and do whatever you want by controlling different parameters like temperatures, pressure, so on and so forth. Yes, MBE has a lot of advantages, but as I said, if we consider only epitaxial structures. Supposing if you want to have polycrystallines or some, amorphous, then you can go with another growth techniques. Yes.
Next question is, what book should a student refer to study molecular beam epitaxy?
Yeah, there are several standard textbook, but as far as my experience is concerned, I find it a little, you know, what to say. I find it a little difficult to understand when I start working on MBE. So what I did and what I could encourage you is that you can refer to some of the PDF documents that you can get it from the internet. Some of the labs, they are writing nicely, which are very easy to understand. However, as far as my experience is concerned, I think MBE has to be understood by going into the real ground, meaning growing some samples, working on it. Yeah, it is a gigantic facility. It's a very big a big instrument for growth, for for crystal growth. So yeah, I think, yeah, reading as well as going into the real ground would help in understanding MBE growth techniques. Yes.
Any way to calculate the TDD of the epilayer, TEM or XRD?
Yes, definitely. Actually, as I said, the whole purpose of this talk is that sometimes, as I said, we need to correlate the result that we get in TM by using XRD and other techniques, so on and so forth, so as to look at the consistency of the result. Because as I said, we need to look for the global result of some particular heterostructures. So yeah, even you may get some numbers by using TM, but I would always encourage anyone to cross check the result with some of the XRD technique for trading dislocation density or any dislocation density measurement. Supposing you may use at pitch a density measurement system by using some microscopy technique. But however, you have many dislocations which are not trading to your surface. So in that case, it would be wise, meaning it would be very interesting if you can check with your XRD. So XRD, by using XRD, you can quantify your trading dislocations by by fitting your intensity profile. So yeah, if you look at many of my works are with calculation of trading dislocation density, but in our case we rule out, or we see in many of the trading dislocation density calculations, they fit the intensity profile by using a Gaussian convolutions. So however, you need to fit all those intensity tails by using that any maybe it Gaussians or another convolutions. So we have borrowed another fitting method which were used for hexagonal Warzite structures. Actually, these works were done by Kaganer and his group in Germany, and
we brought it, meaning we convert it in such a way that we can use for, cubic systems, because as I said, you need to fit even, intensity tails, the tails which are, which are caused by the dislocations or the strain built by the dislocations. Basically without fitting the tails of your intensity profile, then you cannot get accurate result of your dislocation density. So yeah, that would be taken into account. Yes, we have done a lot, and also people have done a lot of work in trying to quantify the dislocation density by using XRD. In fact, people are more, people rely more on the calculation of dislocation density by using XRD. As I said, you can have a global pictures about the density of dislocations by using XRD. Yes, you can read a lot of literatures, yeah, starting from Williamson whole plot to even Kaganer method.
Very well said. Can you give insights on other heterostructures like gold, silver, tellurium, gold?
Actually, that's beyond my topic, and yeah, but I think you may find a lot of literatures, but since I'm working on group 4 or integration of group 4 on 3-5 systems, I have no much idea about gold, silver, so on and so forth, but I think you can find many literatures. But as far as my experience is concerned, I can I I I didn't find any group working on these heterostructures, but however, you can find some groups who are working on low dimensional, like quantum dots, so on and so forth. Yes, with silver nanoparticles or gold nanoparticles, which you can have quantum dot size for that. Yes.
Okay, the last question for today's talk is, what are your wishes to current research students?
Yes. So I wish them to do very hard work with with interest. Meaning, what I'm trying to say was that people who are coming to research community should be really interested. So basically, it means that they should have academic integrity. So academic integrity is like accepting the fact that we are doing work which can benefit others, and this is our work and we need to focus on our works. So uh, say for example, see, my work is directly related to community because I'm working on the growth of heterostructures for photonic device, but there are many students, research scholars whose work are indirectly affecting the community. Meaning, basically, say for example, someone is working on theoreticals, and for them, it will never directly, in most of the cases, it may not directly affect the community. Say something that I really like about PhD thesis defense was that there is one questions that one can get prepared before he started defense. So that questions is, what would be your work, what would your work contribute to the community? So see, there are many research scholars whose works are not directly affecting the community. So they used to answer like this. See, my work is a theoretical one, and it's very mathematical, and it's a mathematical concept, and so it may not be useful for the community directly as of now, but maybe after 20, 30, 100 years, people may cite my papers, so eventually people may have some new ideas. So yeah, in that ways it may be important. So what I'm trying to say is that when you are doing research, it may not be important for the community directly, but accept the fact that whatever is what anything whichever is important indirectly is very, very interesting, and which you can never deny the importance of it. So yes, as a research scholars, I wish them to to accept the fact that we are doing work for the development of our countrymen, our friends, or our community, but in some cases it may not directly affecting the society, but we need to accept the fact that we are doing a very focused work which will eventually lift the society. Yes, and also something that I would like to encourage, even I myself also, I'm still encouraging myself. So I would always would like to encourage you to look at the problems from a very basic science or basic physics. Say, for example, starting from Coulomb's law. See, sometimes as a research scholars, we used to take many of the result intuitive in the sense, there are some published data, there are some published result, and since people have already done, we just take it as these were all done and all correct. But in many cases we need to revisit, we need to ask the questions by using some basic science, and that will help a lot. And in that way our careers in research will eventually help. Yes.
Very well said. On behalf of CRNTS, I would like to thank Professor Krista R. Kiante for a superb talk on defect structure of germanium 111, on epitaxial gadolinium oxide 111, on silicon 111 heterostructures grown by molecular beam epitaxy. We are really grateful to Professor Krista R. Kiante for answering the questions. I would also like to thank our head, Professor Anil Kotantarail, for his continued support in this webinar series. And last but not the least, I thank all the participants for attending this webinar and making this event successful. A link for the feedback form is shared in the question and answer section. Please fill the form. Your valuable inputs are important to us. The registration link for the next webinar is now open on our website. The upcoming talk is on processing structure-performance relationship of graphene and its variants towards electrochemical lithium storage by Dr. Farzana J. Sonia. I request you all to join us for our next talk. Once again, thank you for all making this webinar successful. Stay healthy and safe. Jai Hind.